Yo, what's up, everybody? So this is kind of a part two to the previous video where we were kind of talking about what happens when you take anatomy and physiology as a course and you get into talking about the skeletal system. So last time we talked about, I think one of the last things we talked about were bone cells and the four different types of major bone cells and what they do. And in this particular video, we want to kind of cover some other things. Like we want to kind of talk about hormones, we want to talk about bone formation, and then we want to talk about what happens when you break a bone. So let's get into it. So first thing I want to talk about are two terms that people at times get confused when they get into this material, and that's calcification and ossification. Calcification is the process of depositing making calcium deposits into bone tissue. And then ossification is actually the formation and development of bone tissue. Now, I know they sound the same, but there's a lot different about them. So let's start with calcification first. So with calcification, what's going on is we're depositing these things called hydroxyapatite crystals. And these crystals are primarily made up of like calcium and phosphate, right? And if you're trying to like understand what's going on, this is what's happening. So essentially what's going on is our cells deposit this crystal substance onto protein fibers of collagen. To give you a better idea of what that kind of looks like, think about this. Have you ever made rock candy? Like, have you ever made like sugar candy? Some people call it rock candy, some people call it sugar candy, some people call it sugar crystal candy. There's a lot of different names for it. But basically, what you do is you take, you need a mason jar, a straw, some string, water, and some sugar. And if you want to get all fancy with it, you take some edible food coloring or edible food sprinkles. You take the string, you dip it in some water, get it wet, then drag it through some sugar, and then tie it to the string, and then suspend it in the jar. And then you fill the jar with sugar water. And then you put some edible food coloring or food sprinkles in there and mix it all together. And then you leave it for several days. And when you come back to it, you pull the stringer out and you'll have rock candy. Like literally, you just made rock candy colored, whatever color you put in that jar, you'll have a colorful rock candy that's there. And the premise behind it is this. When you dissolve sugar into water, it's dissolved, but the molecules are still in the water. They're just diluted in the water, right? They're soluble. They're diluted in the water. If you stick your finger in the water, you can't feel the sugar crystals. But if you take a solid substance like the string that's been coated in sugar, and you allow the sugar molecules that are floating around the water, as they bump into that string of sugar, they will attach to one another and then they'll solidify. So originally the sugar in the water was dissolved. It was soluble, it was dissolved, it's floating around in the water. Once it bumps into a solid sugar molecule, they will go from being dissolved in the water to solidifying and becoming a crystal. Those crystals will form on that string. That's similar to what happens with calcification. What winds up happening is you release this hydroxyapatite, which would be the sugar, and then the collagen fibers would be the string. And what winds up happening is you have this hydroxyapatite crystals forming on the string, making the rock candy, which in our case would be the calcified bone tissue. And that's how your bone tissue becomes hard. That's how it becomes dense and rigid, is because of that calcium and phosphate that's been added to the collagen protein fibers. In order to make calcification, like the whole process, actually work, you need a few things. So, for example, you're going to need some vitamin D, because vitamin D is going to actually come in, and that's going to ultimately become calcitriol, which we're going to talk about that today. And the calcitriol is going to increase the uptake of calcium and phosphate from your diet, and allow you to be able to make more of this bone tissue. And then the other thing you're going to need is vitamin C, because you use vitamin C to make collagen fibers. So that's going to be more of the string. Then you're going to have the calcium and the phosphate, which are going to ultimately become hydroxyapatite, which is the crystals that you're going to attach with the string or the collagen fibers. And once you have all of that, now you got calcification. So calcification is like a crystallizing process. It's what makes the bone tissue hard and rigid. Ossification is more like bone modeling, right? With ossification, what winds up happening is we start off with some type of connective tissue, and we transform that connective tissue into an osseous model. So calcification, you kind of started with nothing, and now you're building something. But ossification is we start with a one type of connective tissue, and we transform that connective tissue into osseous connective tissue, into bone connective tissue. As a matter of fact, once you do ossification, we actually use calcification to make the new osseous tissue hard and rigid. So you can kind of think of it in one way is we usually don't do one without the other. We start off with some ossification, and during ossification we do calcification. So with ossification, there's like two different types. There's intramembranous and then there's endochondral. Intramembranous is when we use like some type of membrane, some type of thick or thin yet flat membranous connective tissue, and we create osseous centers, ossification centers within that tissue. They spread out and they cause calcification of the immediate area, and it spreads from there with like little tendrils reaching all out until they've turned this flat piece of connective tissue into bone tissue. Typically we see intramembranous happen in flat bones. So intramembranous is extremely important for the skull. So when you talk about a baby having soft spots in their head, those soft spots are called fontanelles, and they are areas where the flat bones of the skull has not completed the calcification process. They're still undergoing intramembranous ossification. So there's like spaces around the skull bones that are still soft and pliable. They've not calcified yet. So it's still undergoing that whole process. Endochondral ossification, if you haven't been able to tell from the name, endochondral, inner, chondral is talking about, chondro is referring to cartilage, endo is talking about inner. So what winds up happening is we have these cartilage models, and inside the cartilage models we begin to ossify those spaces inside there to make it become bone. So this can start early in the development process. You're talking like, the endochondral ossification really starting with the cartilage models before you're born, and then kicking in full gear just weeks after you're born, continuing that process until until you have the skeleton that you're going to continue to grow with and develop over time. Endochondral ossification primarily functions to grow the majority of the bones of your skeleton, versus intramembranous. Intramembranous is like your skull and your sternum, your mandible. It primarily, intramembranous ossification handles like flat bones and irregular bones, versus Endochondral ossification handles things like the bones in your fingers, your hand, your arms, your legs, your feet, your toes. A lot of the other bones of your body, actually the majority of the bones of your skeleton, really. Um, and they all kind of follow the same general pattern. Uh, there's ossification centers that happen, and the bones are trying to get longer, um, and merge and merge to not merge, but they're trying to get longer. They're trying to elongate and grow with you. The pattern that they're going to follow is pretty much the same. The rate of growth is going to be different. It's going to be dependent upon people. I um, I don't consider myself very tall, but then again, I come from a family that happens to be a grove of trees. So everybody in my family is considered tall. I have aunts that are my height, and I played basketball. A lot of people in my family play basketball just because of our height, right? Um, for us, our bones grow very long, right? Um, for some people, genetically, their bones may not grow as long, so they are of different heights, right? Um, Another thing that you will study when you're talking about the skeletal system in an anatomy and physiology class is bone remodeling. So your bones are constantly remodeling themselves, and how they do this, how often they do this, the benefit to you when they do this will depend on your activity and your diet and your personal health. Because research has shown that your entire skeleton, that you will replace up to 20% of your entire skeleton every year. So literally within 365 days, within 12 months, you will have replaced somewhere around 20% of all of your bone tissue with new bone tissue. Now, can you speed that up? Probably so. Because your bone tissue is directly correlated to your diet and your activity. So the more active you are, like with strength training and exercise and resistance training, the stronger your bones will be, the more active the cells will be, the more active they will be in repairing and replacing dead and worn out bone tissue. But the less active you are, the less that you actually get around and do, um, the less active your bone tissue is going to be, right? Which can lead to brittle bones, and can lead to bone tissue that's a little more that requires more repair. Um, when it comes to your bone tissue knowing what to do and when to do it, um, in the last video I talked about the fact that your bones are like a bank, that you can actually deposit minerals into your bone bank, and then you can make withdrawals from your bone bank. It knows to do that for a number of different ways. And one of the ways that it does that is through chemical messengers, which we call hormones. Two of the ones that I want to point out are calcitriol and parathyroid hormone. Now, calcitriol has a pretty interesting process of how it comes about its existence. It all starts with sunlight. If you go outside and you spend time in the sun, your skin cells will then be able to use the UV rays from sunlight to convert um, a steroid into vitamin D3. So there are different types of vitamin D. Specifically, the one that your skin cells make is vitamin D3. So there's a steroid that your skin cells will make. They will then, in the presence of UV rays, convert it into vitamin D3. Then they will ship that vitamin D3 ultimately to your kidneys and your liver, and your kidneys and your liver will then convert that to calcitriol. Is there a biochemical pathway? There is. If you'd like to hear more about that biochemical pathway, leave a comment below, and I'll try to get a video put together for that. But for the sake of time, so we take that calcitriol, and that calcitriol acts like a hormone, And that calcitriol primarily targets the small intestine. Now, the reason why it targets the small intestine is because your small intestine is a part of your digestive system. And 85% of everything that you digest and absorb happens in the small intestine. That's why your small intestine is so long. The average human small intestine is close to 20 feet long. And so it's that long because there's a lot of absorption and digestion that needs to take place. So whatever meal you eat today, it's going to process that, break that down, and try to digest it. And 85% of that digestion happens there. Well, since so much of that digestion and absorption happens in the small intestine, that's why calcitriol is specifically designed to target the small intestine so that it makes sure that it puts extra effort into absorbing calcium and phosphate. Why? Because once you absorb that calcium and phosphate, it goes into your bloodstream, and whatever is in your bloodstream, the cells of your body have direct access to. Therefore, now your cells can use calcium and phosphate as well as bone tissue. Now your bone tissue can then take that calcium and phosphate and upload it into the bone tissue, deposit it into the bone tissue so that you can make a withdrawal later on. The second hormone I want to talk about is parathyroid hormone. Parathyroid hormone, not to be confused with thyroid hormone. Two totally different organs, two totally different hormones. Parathyroid hormone is funny because parathyroid glands come in pairs. They always come in pairs. And they're actually located behind your thyroid gland. That's why they call them parathyroid glands, which produce parathyroid hormone, because they're in pairs located to the posterior of your thyroid gland. And they make parathyroid hormone, PTH. And PTH increases calcium levels in the blood, which means that PTH will then tap into your calcium banking account, which is the bone tissue, and it will cause the bone tissue to release calcium, would make a withdrawal of calcium from the bone tissue into the bloodstream so that your body cells can use that calcium for whatever it needs it for. So calcitriol increases blood calcium levels. Parathyroid hormone, it increases blood calcium levels as well. There's a third hormone, and I noticed that some textbooks don't talk about it anymore. But when you get to the endocrine system, we talk about it. So I'm kind of confused why they don't talk about it in the skeletal system chapters anymore. And that's a hormone called calcitonin. And calcitonin tones down calcium levels. It actually does what is needed to do to bring calcium levels down in the blood. And it actually leads you to take calcium out of the blood and put it into your bone tissue. Whereas parathyroid hormone causes you to take calcium out of the bone tissue and put it in the blood to raise blood calcium levels. The last thing I was going to talk about, and I'm really running out of time here, is talking about fractures when you have a fracture that heals. At some point in time, we stopped saying broken bones and we started using fractures in lecture and in textbooks. It used to be, back in the day, they used to tell you that you could have a broken bone or you could have a fracture, and that a fracture was like a small break, that a broken bone was a big break. And then they stopped doing that. Then they just said, nope, all broken bones are fractures. It's just fractures. And you have different types of fractures. If you've never done this before, go and study the different types of bone fractures. It's not for the weak. It's not for the faint of heart. I'm telling you that now. It's definitely not for the faint of heart. If you want me to do a video on bone fractures, let me know in the comments, and I'll try to put one of those together next time. But bone fractures are amazing. Like a compound fracture is when the bone breaks, but then the bone breaks the skin. I saw that in a football game when I was in high school. This guy got tackled, and it was, man, it was it was pretty gross to actually see it. It's one thing when you're watching a horror movie and see it. It's another when you're standing right there on the football field and you see it happen right in front of you. Compound fracture, comminuted fractures. There's all types of different fractures, but for the most part, basically, with a bone fracture, you because bone is tissue, it's living tissue. You would expect it to, experience the same things that a lot of tissues do. And to be more specific, bone is a type of connective tissue. So the same thing that you would see happen to damage connective tissue is the same thing you should expect to happen to damage bone tissue. Like, the first thing that happens is it bleeds because it's a living tissue. Like, when we think about bone tissue, unfortunately, we think of it as this inanimate thing that's not alive, right? And that is like a rock or something like that. But unfortunately, it's not a rock. It's alive. It's living tissue. So it's vascularized. It's got lots of blood vessels in it. So when it breaks, it bleeds. It causes a hematoma to form, and then the body has to go through a process of cleaning all of that up because it's a big blood clot that's there, and it's swollen. There's inflammation that takes place. So it has to clean up both the dead blood tissue as well as the broken bone tissue that's there. It's got to clean all of that up and put all that away. But then now there has to be something put there that's temporary, especially if it's compact bone. So what we end up doing is we don't move in with regular bone tissue right away. We move in with fibrocartilage. And whatever bone was there, we replace that with fibrocartilage in that space. And then cells move in to convert that fibrocartilage into regular bone tissue. Because remember, we just talked about intramembranous and endochondral ossification and calcification. So that process happens there as well. So first we put that cartilage model in there to bring some stability, and then we convert that cartilage over to bone tissue, and then we wind up having like this bony callus there. So like, for example, on my ring finger on my left hand, I dislocated this finger in a game. Not only did I dislocate this finger, but I broke the finger as well. Yeah, I was going for a superlative in this particular situation. Well, while I was in the game, I was amped up on adrenaline, so I popped my finger back into place to stay in the game. But I didn't know that the bone was broken. So once the game was over and everything, I was able to get in to see a doctor to get it x-rayed. It had formed a callus. So that swelling led to, excuse me, I said that wrong. The swelling ultimately led to a callus. And so what it ended up doing was just made a bulge on my finger. And that, over time, your body will remodel that space. It'll break down the extra swelled area. It'll try to bring everything back into the normal shape. But it took my finger a long time to do that. So wearing things like gloves and rings and stuff like that on my finger was extremely difficult to do because of the swelling. All right, hopefully that kind of explains some things, put some things into perspective. If you like this video, make sure you like it, share it with a friend or another classmate. If you haven't already, subscribe to the channel. Leave in the comments some other things that you might want us to make some videos about. And I'll see you next time when we talk about joints.